Human Physiology, Chapter 2, Homeostasis. The human organism consists of trillions of cells, all working together for the maintenance of the entire organism. While cells may perform very different functions, all the cells are quite similar in their metabolic requirements. Maintaining a constant internal environment with all that the cells need to survive, oxygen, glucose, mineral ions, waste removal, and so forth, is necessary for the well-being of individual cells and the well-being of the entire body. The varied processes by which the body regulates its internal environment are collectively referred to as homeostasis. What is homeostasis? Homeostasis, in a general sense, refers to stability or balance in a system. It is the body's attempt to maintain a constant internal environment. Maintaining a stable internal environment requires constant monitoring and adjustments as conditions change. This adjusting of physiological systems within the body is called homeostatic regulation. Homeostatic regulation involves three parts or mechanisms. 1. The receptor. 2. The control center. And 3. The effector. The receptor receives information that something in the environment is changing. The control center, or integration center, receives and processes information from the receptor. And lastly, the effector responds to the commands of the control center by either opposing or enhancing the stimulus. This is an ongoing process that continually works to restore and maintain homeostasis. For example, in regulating body temperature, there are temperature receptors in the skin, which communicate information to the brain, which is the control center, and the effector is our blood vessels and sweat glands in our skin. Because the internal and external environments of the body are constantly changing, and adjustments must be made continuously to stay at or near the set point, homeostasis can be thought of as a synthetic equilibrium. Since homeostasis is an attempt to maintain the internal conditions of an environment by limiting fluctuations, it must involve a series of negative feedback loops. Positive and negative feedback. When a change of variable occurs, there are two main types of feedback to which the system reacts. Negative feedback, a reaction in which the system responds in such a way as to reverse the direction of change. Since this tends to keep things constant, it allows the maintenance of homeostasis. For instance, when the concentration of carbon dioxide in the human body increases, the lungs are signaled to increase their activity and expel more carbon dioxide. Thermoregulation is another example of negative feedback. When body temperature rises, receptors in the skin and the hypothalamus sense a change, triggering a command from the brain. This command, in turn, affects the correct response, in this case, a decrease in body temperature. Home heating systems versus negative feedback. When you are at home, you set your thermostat to a desired temperature. Let's say today you set it at 70 degrees. The thermometer in the thermostat waits to sense a temperature change either too high above or too far below the 70-degree set point. When this change happens, the thermometer will send a message to the control center, or thermostat, which in turn will send a message to the furnace to either shut off if the temperature is too high, or kick back on if the temperature is too low. In the home heating example, the air temperature is the negative feedback. When the control center receives negative feedback, it triggers a chain reaction in order to maintain room temperature. Positive feedback. A response is to amplify the change in the variable. This has a destabilizing effect, so it does not result in homeostasis. Positive feedback is less common in naturally occurring systems than negative feedback, but it has its applications. For example, in nerves, a threshold electric potential triggers the generation of a much larger action potential. Blood clotting, in which the platelets process mechanisms to transform blood liquid to solidify, is an example of a positive feedback loop. Another example is the secretion of oxytocin, which provides a pathway for the uterus to contract, leading to childbirth. Harmful positive feedback. Although positive feedback is needed within homeostasis, it can be harmful at times. When you have a high fever, it causes a metabolic change that can push the fever higher and higher. In rare occurrences, the body temperature reaches 113 degrees Fahrenheit, or 45 degrees Celsius, and the cellular proteins stop working. Then metabolism stops, resulting in death. Summary: sustainable systems require combinations of both kinds of feedback, generally with the recognition of divergence from the homeostatic condition. Positive feedbacks are called into play, whereas once the homeostatic condition is approached, negative feedback is used for fine-tuning responses. This creates a situation of metastability, in which the homeostatic conditions are maintained within fixed limits, but once these limits are exceeded, the system can shift wildly to a wholly new and possibly less desirable situation of homeostasis. Homeostatic systems have several properties. They are ultra-stable, meaning the system is capable of testing which way its variables should be adjusted. Their whole organization, internal, structural, and functional, contributes to the maintenance of balance. Physiology is largely a study of processes related to homeostasis. Some of the functions you will learn about are not specifically about homeostasis. For example, how muscles contract. But in order for all bodily processes to function, there must be a suitable internal environment. Homeostasis is, therefore, a fitting framework for the introductory study of physiology. Cruise control on a car as a simple metaphor for homeostasis. When a car is put on cruise control, it has a set speed limit that it will travel. At times, this speed may vary by a few miles per hour, but in general, the system will maintain the set speed. If the car starts to go up a hill, the systems will automatically increase the amount of fuel given to maintain the set speed. If the car starts to come down a hill, the car will automatically decrease the amount of fuel given. It is the same with homeostasis. The body has a set limit on each environment. If one of those limits increases or decreases, the body will sense and automatically try to fix the problem in order to maintain the preset limits. This is a simple metaphor of how the body operates. Constant monitoring of levels and automatic small adjustments when those levels fall below or rise above a set point.